Swayam Prabha. Digital India. Educated India.
So we'll start off this lecture with recap of bipolar and MOSFET devices when they are used as an amplifier. I will go through a generic amplifier input-output definition, different definitions of the voltage gain of the amplifier, and then we will start with a single transistor amplifier. Going forward, we are going to build on this and we are going to go through various configurations using bipolars and MOSFET side by side to understand how each amplifier works. And from that, we will develop our insights for more complex circuits. So pay close attention because these are all basics you need to really internalize. So in this lecture, we will start with recap of BJT and MOSFET operation. So BJT can be used as an amplifier when it's in active region. And what is the definition of active region? When VBE is greater than 0.7 volts and VCE is greater than or equal to 0.3 volts. So the collector current is flowing in this fashion, and we can also say that VBC is less than or equal to 0.4 volts. Key point is base to emitter junction is forward biased, carrying current. However, base to collector junction is not completely forward biased. It has to be reverse biased, but in the worst case scenario, it should be slightly forward biased. Ideally, we would like it to be reverse biased, but until this condition, we can call it the transistor is in forward active region. Collector current is given by IC is equal to IS exponential VBE divided by VT. In this mode, the small signal model of the bipolar junction transistor, please draw it yourself. Between base to emitter, we have R pi, and here is our small signal VBE voltage. From collector to emitter, we have the current flowing, which is GM times small signal VBE voltage. And then from collector to emitter, there is Rout, output resistance of the device. R pi is given by beta divided by GM. Beta is in the range of 50 to 100. Transconductance GM is given by IC divided by VT. In this case, IC is the DC value or DC operating point, and VT is the thermal voltage KT over Q. It's important that you don't confuse between VT, which is KT over Q for bipolar transistor, versus VT or VTH for MOSFET transistors, which is a threshold voltage. Output resistance Rout is equal to VA divided by IC. VA is the early voltage. Now we are going to plot the characteristic. So I'm plotting large signal characteristics of the bipolar transistor. On the y-axis I'm plotting IC, and on x-axis I'm plotting VBE. So since base to emitter junction diode is forward biased, we will see something like this. And if you bias your diode at certain point, let's say over here, then that would be your operating point. And if we apply a small signal AC voltage, VBE, around this point, then we see this is the slope, that would be your transconductance GM. One important aspect I would like you to think about is, would you see an inversion over here? The answer is no, there will not be an inversion, and let me explain why. VBE, small signal VBE, which is over here, that is changing in this fashion. If VBE increases, then the collector current, does it increase or decrease? That's the first question. The collector current will increase. Hence, there is no inversion when we plot the characteristics between VBE and IC, small signal. So what we expect here is, we will expect characteristics that looks like this. This is an important point because we are used to thinking there is an inversion going from base to collector. However, the question I'm asking you, specific question is important here. What I'm asking is, if VBE is changing in this fashion, if VBE increases, then collector current should also increase. The inversion we see is because of the resistor that we have over here at the collector, and this is your VDD. So if VBE goes up, then the collector current will go up, IC will go up. However, the potential, output potential, is equal to VDD minus ICR. And that's the reason we are seeing the inversion. When we say that there is an inversion from base to collector, this is the reason. When you're looking at the output voltage, then there is an inversion. But when you look at from voltage to current point of view, there is no inversion. Somebody can trick you in this particular question, and your fundamentals should be sound. So reiterating again, when you look at it from base to emitter small signal voltage to small signal current, IC, there is no inversion. However, if you look at base to emitter small signal voltage to the collector voltage, then there is an inversion because of VDD minus ICR equation. Now let's repeat the same exercise for MOSFET transistor. MOSFET transistors can be used as an amplifier when it is in saturation region. So let's define the state there. So from DC biasing point of view, VGS should be greater than VTH, which is the threshold voltage, and VDS should be greater than or equal to VGS minus VTH. And this is our definition of saturation region. The DC current is ID is given by half mu n Cox W by L times VGS minus VTH square. For all hand calculations, we generally use this simple equation, and if you want to consider the second order effect due to channel length modulation, then you will add 1 plus lambda VDS. Now for AC analysis, the small signal model looks like this. So GM VGS is the current source flowing from drain to source. Rout is the output resistance of the MOSFET. Transconductance GM is given by 2 ID divided by VGS minus VTH. Again, when we are calculating GM, we are using ID or VGS. These are DC values. And Rout, output resistance, is given by 1 over lambda channel length modulation coefficient times ID. ID here also is a DC value. Just like what we did in the bipolar case, let's look at the transfer characteristics one more time. So I'm plotting large signal drain current on the y-axis and large signal VGS on the x-axis. And we know when VGS is equal to VTH, then the transistor is just beginning to conduct. So the current is 0 at that point, let's say, right here. And then it has a square law operation. So it looks kind of like this. Let's say we are operating at this place. This is our DC operating point, VGS. And this is our DC operating current ID. If you draw a tangent over here, that would be the slope, which would give you GM, the transconductance. Now if we apply a small signal VGS over here, the same considerations as we talked in BJT's case, there is no inversion when we look at it from the gate to source voltage VGS to drain current. So in this case, you will see waveform that's a little bit exaggerated and looks like this. So there is no inversion from gate to source voltage to the drain current. However, there is inversion when you just look at the drain voltage, because we again have V output at drain is given by VDD minus ID times R. And that generally happens when you have a resistor, and this is your VDD. When you look at the output voltage, there is inversion. However, if you just look at the drain current, then there is no inversion. One more thing to note here is, what is this parameter over here? This is VTH. The green arrow showing is VGS minus VTH, and we know that that's our DC biasing VDSAT. Now we will start with a new topic, amplifiers. Let's look at amplifier as a building block first. We generally show amplifier as a triangle. Typically the amplifier is driven by a preceding stage, and amplifier drives the next stage. So the preceding stage, we can model it as some kind of source, AC source with its own source resistance, and the amplifier is driving next stage, which has a RL as a load resistance. We can say that input current going into the amplifier is II, and output current coming out of the amplifier is IO, and V0 is the voltage at the output of the amplifier, and VI is the voltage at the input of the amplifier. Again, we are talking about AC analysis here. Now we can get into the details where we will show more detailed model for the amplifier. So the circuit inside the box is the amplifier model. We are showing input resistance of the amplifier as Rn, and voltage across this input resistance is Vi, and at the output we have output resistance Ro. This Ro is driven by AV0 Vi, whereas AV0 is denoting the gain provided by the amplifier. So let's go through some definitions. The input resistance Rn is given by, let's say II is the current going into the amplifier, then input resistance Rn is given by Vi divided by II. In this case, we are considering amplifier to be a unilateral amplifier. What that means is Rn is independent of RL, and there is no internal feedback inside this amplifier. The open circuit voltage gain of the amplifier is given by AV0, which is V output, which is shown over here, V0 divided by Vi. And this is under the condition RL is equal to infinity. Since we are talking about open circuit voltage source here, this is the definition AV0. What is Vi? Vi is given by resistive divider. Let's call the source resistance as Rs and source as Vs. So Vi is given by Rn divided by Rn plus Rs times Vs. Similarly, we can write V0 is equal to RL divided by RL plus R0 times AV0 times Vi. Now a few definition. The terminal gain AV for the amplifier is given by V0 divided by Vi, and that is given by AV0 times RL divided by RL plus R0. Once again, the definition here is slightly different. When you talk about open circuit voltage gain, then RL is infinity, and that is AV0. With some RL, then we are defining terminal voltage gain as of the amplifier as by this expression. So terminal voltage gain takes into account the effect of the load resistance RL. However, in this case, the denominator is still Vi, which is at the input of the amplifier. And when we look at the overall voltage gain, which means the output voltage VO and source voltage Vs, that would be your overall voltage gain. That is given by the following expression. Let's write that. GV is equal to, so first we have the voltage divider at the input, which is Rn divided by Rin plus Rs multiplied by AV0 multiplied by RL divided by RL plus R0, which is V0 divided by Vs. So this is just terminology for you. The reason for this terminology is you cannot just look at an amplifier in isolation. You have to make sure that your amplifier is driven correctly, as well as your amplifier is driving a proper load resistance. The input resistance of the source as well as the load resistance will also affect the gain of the amplifier, and we're going to go through an example of that. Now let's look into calculating output resistance, RO, of the amplifier. So if you look at the amplifier in this fashion, then to calculate the output resistance, we would apply a test voltage source VT like this, and we would measure what is the test current IT flowing into the amplifier. And when we are doing that, we will make sure that all the independent voltage sources, they are connected to 0. So in this particular case, Vi would be connected to 0, or Vs will be connected to 0. The output resistance RO is given by Vtest divided by Itest. So Rin and RO are going to have an important effect on the overall gain, and we should never miss them. Let me go through an example with you so that you will understand the importance of these parameters. Let's say we have a microphone amplifier, and I'm going to give you microphone amplifier with Rin of 2000 ohms and Rout of, let's say, 20 ohms, and voltage gain AV0 is given to be 10. So this amplifier, we expect it to provide a gain of 10, factor of 10. Let's see if we put the details, what happens. Let's say we pick a microphone which can be represented with a resistance of 200 ohms. So this is what we started off with. This is driving our amplifier. So the magenta box is our amplifier. Rin is 2000 ohms, AV0 times Vi, and R0 is equal to 10 ohms. Let's say we were driving a speaker using this amplifier. So if you're a speaker enthusiast or a music system enthusiast, you know that the speaker resistance is something like 8 ohms, maybe 4 ohms or 8 ohms. Let's pick 8 ohms here. And now let's compute the overall gain, GV, from the microphone all the way to the speaker. What are we going to get? GV is equal to, first of all, we have VRI, which is 2000 ohms divided by 2000 plus 200. That would be our first voltage divider. So Vs to Vi, this is the expression, and then we multiply by AV0, and then we multiplied by 8 ohms divided by 10 plus 8 ohms. Sorry, I made a mistake here. This should have been 20. So this is 20 ohms and this is 20 plus 8 ohms. So this is going to be equal to 2000 divided by 2200 multiplied by AV0, which will be 10 multiplied by 8 divided by 28. And if you compute this, you will see that this is 2.6, nowhere close to factor of 10 that we were expecting. So I'm giving you this distorted example just to show you the importance of what is driving your amplifier and what your amplifier is driving. So both these facts are very important and they play a crucial role in achieving the desired gain. In this particular case, the output resistance that we were driving was too low, and as a result of which we lost most of our gain right there. If we look at a generic case, then you will see that, say this is our amplifier, it has some input resistance, output resistance, and is driven by another amplifier which has its output resistance, and that connects over here, and this drives the next amplifier. RO of the previous stage, output resistance of the previous stage, becomes source resistance for us for the amplifier under consideration, as well as Rin of the next stage becomes RL for us. So next stage Rin will look like a load resistance for us. So if you have amplifier A1, A2 and A3, and you were expecting gain of A1 times A2 times A3, that is not entirely true unless you take into account the effects of the interfaces. So interface termination, you have to look into it carefully before you can comment on the overall gain. So after this generic discussion of the amplifier, let's get into transistor level amplifier. This discussion is going to become segue for variety of amplifiers we're going to discuss in next few lectures. And in this discussion, we are going to look at both bipolars and MOSFET amplifiers. So the first amplifier we'll start off with is a common emitter or CE amplifier. As a starting point, we will start with idealized circuit to understand the contribution from the transistor itself only. First of all, why is it called a common emitter amplifier? The reason is we are applying input between base and emitter, and we are looking at the output between collector and emitter. So between input and output, emitter is common, and hence we call it common emitter amplifier. The current source, capital I, is a DC current source. Just like a DC voltage source, which represents the battery, VDC, which we apply to the supply, VCC, you can also get a current source, which is a DC current source. I'm going to show you how to implement that. So in this particular case, we have a current source I. First thing we are going to do is a AC analysis circuit for this. Whenever we do AC analysis, what do? We short all the DC voltage sources and open all the DC current sources. So in this case, the AC analysis circuit is going to look like this. Really simple. In this case, I'm just showing you with the transistor in the picture, and it would just look like this, and we will have only VI going in. So this is your AC circuit. Current source I is open because it's a DC current source, and VCC, you can connect it to ground, but it doesn't come into play here. What I would like you to do is pause the video now and on your own draw the small signal model of this particular circuit. I'm assuming you have drawn this exact same circuit. So I'm substituting for our transistor Q1 with its small signal model right here. What is R pi? R pi is given by beta over GM. GM is given by IC over VT, and output resistance R out is given by VA over I. Reiterating again, the current I is the DC value. In this case, beta we know is the transistor parameter, also VA is a transistor parameter. What is the input resistance of this amplifier? Rn. You can tell if you apply an input source, then the resistance, the only resistance you see looking into this base terminal is going to be R pi. So the input resistance Rn is given by R pi. So this would be your input resistance. To compute output resistance, I'm going to mark it in yellow. What we will do is we will connect the input, independent input voltage source, Vi, we will connect that to ground. As soon as you do that, VBE will go to 0 and this current source will become 0, which means it's open circuited. Now you can quickly tell that our output resistance is going to look like nothing else but R out of the transistor. From this we can say that output resistance of this amplifier is equal to the output resistance of the transistor, R out. What is the voltage gain of this amplifier? The voltage gain is given by V out divided by V in, and that is equal to GM times R out. And there should be a negative sign because of the direction of the current GM. So whenever we look at the voltage gain from base to collector, it's negative. Let's substitute the values. What is the value of the GM? Is going to be I divided by VT, thermal voltage, multiplied by VA divided by I. So I will get cancelled and this will look like minus VA divided by VT. As you can see, given a bipolar transistor, the gain is pretty much fixed. VT is KT over Q, which is 26 millivolts, and VA is the early voltage of the transistor, which could be 100 volts or so. So this looks great. We get a large gain. Unfortunately, the stage has to drive some load resistance. So when you have a load resistance connected to the output, this equation will modify as follows. So if you have a load resistance RL, then your voltage gain will be minus GM times RO parallel RL. If RL is small, then the voltage gain will be approximately GM times RL. One quick thing to note here is, how do we get this current source I, DC current source? Using another bipolar transistor, what you could do is, follow my train of thought, we could simply get a PNP transistor and we can connect some kind of DC voltage source plus minus VEB over here. And what does this look like? This represents a current source, because the current which is going to flow through this I is given by IS times exponential VEB divided by VT. Again, these are PNP parameters. So this current is independent of the terminal voltage as long as the transistor is in active region, operating in the active region. And the current value is decided by VEB only. And as long as you make sure that there is no AC voltage applied, it's just the DC voltage there, then the current value I will be constant. This is a good way to implement constant current source. So the overall circuit is going to look like this. This is your VCC, and you start off with your PNP transistor and you apply some constant bias here VEB such that the transistor Q2 is in active region, which will give you current I, constant current source flowing, and that is going to be flowing through our Q1. And here we are going to apply our VI input signal, and we are going to apply V bias. We can also call this as V bias 1, and we can call this on the top as V bias 2. V bias 1 and V bias 2 are DC values which are there to appropriately bias the transistor, and this would be your V out. Vi is the AC quantity. The V bias can be also implemented using a simple resistive divider from VCC to ground, and you can still get your constant current source I that you desire. Now let's do the same analysis for MOSFET transistor. I want you to think about what would this amplifier be called. This is your input and this is your output. Which terminal is the common terminal between input and output? As you would have guessed it, it's the source of the transistor, as a result of which we call this common source amplifier or CS amplifier. We will do exactly same analysis that we did before. I would like you to again draw the model on your own of the transistor, specifically the AC analysis. So for purpose of AC analysis, this would look like this, VI, and this would be your V out. Let's call it M1, and the AC analysis model is going to look like this. This is again small signal model. What is Rin? Resistance looking into the gate, which would be equal to infinite. This should be obvious. And what is R out again? R out would be the resistance looking back into the amplifier. To calculate R out, over here we would connect the input independent voltage source to 0, which will take away the GM-VGS current source, and you will be only left with R out, RO of the device, and that will be equal to, so R out is going to be RO, and that is given by 1 divided by lambda I, lambda being the channel length coefficient, and I is our DC bias currents. What is the voltage gain of this amplifier? Is V out divided by V in, and that is equal to minus GM times R out. What is the value of the GM? 2I divided by VGS minus VTH, and R out is given by reciprocal lambda I. So this will be minus 2 divided by lambda VGS minus VTH. The interesting aspect here is that the voltage gain of MOSFET amplifier is controllable. First of all, there is a lambda part, so we can increase the length. If you increase the channel length, then the gain will go up. Also, if you decrease VDSAT or VGS minus VTH, then gain will go up. In case of bipolar, we don't have any control over the gain. However, you really get a lot of gain in bipolar case because the early voltage is 100 volts or so, and you divide that by 26 millivolts. So that gives you a lot of gain from the transistor by itself. As soon as we have a load resistance here, the voltage gain of this stage will be limited to minus GM RO parallel with RL. Similar to bipolar example, we can implement the current source using PMOS device, and let's see how to do that. If you bias M2 in saturation using a proper biasing voltage source V bias 2 connected from source to the gate, then it's going to provide current which will look like a constant current source because this V bias 2 is a DC quantity. So this is the simplest amplifier with one transistor. We are going to go through many more configurations in the future lectures. Key thing I would like you to remember is the analysis can be a little bit dry going forward, but I would like you to keep your antennas up because we are learning certain patterns as we go through this detailed analysis. First time we are going through the analysis, we are going to go through real details, but after a few patterns are observed, then you should be able to recognize them very quickly when we see complex circuits. And that is what we are going to do. So every time you don't have to do detailed analysis, you should be able to do pattern recognition and you can figure out what kind of configuration, circuit configuration we are looking at, and we can quickly tell what is the gain, what's the input impedance, what's the output resistance, all those parameters we should be able to tell. Thank you.